Hi guys, very early in the morning. It is still dark out, and this is going to be the last two sections of the chapter, purely discussional, no calculations at this time. Ooh, I should take that back. A small calculation, but a nice plug and chug kind of a thing. Effusion describes the passage of a gas through a tiny hole into a vacuum. The rate of effusion measures the speed at which the gas is transferred. The rate of effusion of one gas is inverse to the square root of mass. The rate of effusion of two gases is given by the inverse ratio of the square roots of the masses of the gas particle. What exactly does this mean? A couple of things that come into my mind when I read this. First, a vacuum. That means that there's nothing else in there. Just the gas that you're studying, or gases. Thing number two, bottom line, see this hole here? Fat molecules will take a long time to get through the hole. I mean, read it again. The rate is speed. The rate of the infusion is inverse to the mass. That means that the fatter the molecule is, the slower it's going to be to move through the hole. Nature abhors a vacuum. If this side is all gas particles and this is a vacuum, those gas particles are going to go through the hole into the vacuum. And if you have more than one gas in this chamber, it's going to go through the hole dependent on the size of the molecules. And the fatter molecules will be slower to get through the hole. And this is also at constant temperature and pressure, because diffusion is a little more difficult to study than effusion, because diffusion is in air. Gases diffuse through air. This is a mixture of gases, and the rate of diffusion is the rate of the mixing of gases, and of course depends on distance. So like if you open a perfume bottle in the back of the room, those gas molecules will have to make their way through the air in the room. So you're going to find that it's going to take a little while for the perfume molecules to diffuse through the entire room. No vacuum means you're in air. Lots of delays because you're bumping into all those other air particles. There are 9 different gases in air, so your little perfume molecules have to make their way through all these molecules of gases. It's kind of like going through a maze. I mean, what's easier to go through, a straight line or a maze of twists and turns? Your perfume molecules will have to make their way through a huge maze of other gas molecules. So the diffusion is a little more complicated. Diffusion takes a little slower because of all the obstacles. The path of one particle in a gas. Gases are supposed to move in a straight line. As you know from the kinetic molecular theory worksheet you did, there's supposed to be elastic collisions, which they are, and that's fine. And they should go in a straight line except for one major problem. Take a look at the room around you, if you're watching this at home or whatever, and think about your room in the class. A gas particle cannot move in a straight line because there's so much stuff in the way. They've got other gas particles they've got to get past. They've got cabinets and sinks and desks and books and you that they keep bouncing off of. So they're supposed to move in a straight line, but they don't, and they can't. There's too much junk in their way. Of the two, effusion is the easier one to visualize because it's in a vacuum. And diffusion is in air. So of the two, effusion is the easier one to calculate because you do not have all that extraneous stuff. Also notice that effusion is rate, meaning the speed of the particle, and diffusion is distance traveled. But they are basically calculated the same way. The molar mass inverse. So the rate for a gas is the inverse of its molar mass square rooted. So pretty simple, really. You just kind of plug things in the right place. Give it a little thought. All right, up to now we've been talking about ideal gas. An ideal gas occurs at low pressures and high temperatures. And we've used the ideal gas law. Ideal gas, the reason we like to consider ideal gases at low pressure and high temperature is because the gas molecules themselves will not contribute to the volume of the gas, and the high temperature prevents any attractive or repulsive forces. So we've been working with ideal gas. In reality, real gases have to have a correction factor because real gases at high pressure and low temperature will contribute to the volume of the gas and will experience attractive or repulsive forces, in all honesty. So at high pressure and low temperatures, at high pressure, that means low volume, that means the particles themselves will contribute volume to the overall gas sample. At low temperatures, the particles are moving slow enough where they might actually be attracted to each other or repulsed. So now you're dealing with forces. You're dealing with the forces, and you're dealing with the volume of the molecules themselves. So real gases at high pressure and low temperature have to have a correction factor. Ideal gas is hypothetical. No gas follows the ideal gas law, but many come close at low pressure and high temperature. Problem is, gas particles do have volume. The particles themselves do contribute to the volume of the gas. Gas particles do attract each other. So van der Waals equation corrects for attractive force and particle volume. Van der Waals equation looks like this. Notice its similarity to the ideal gas law. Also notice it's a little uglier than the ideal gas law. And A and B are actually proportionality constants that are indigenous to the particular gas you're looking at. So we have our choice. We either stick with the ideal gases and use Pivnert, or we go with the real gases and use the van der Waals. And A and B are proportionality constants. A for attractive force, B is for the volume of the actual particles themselves, both determined by experiment, and both are different depending on the gas. So again, A and B proportionality constants that are indigenous to a very particular gas species. All right, last thing. Gases at low concentration also will experience relatively few interactions. So this guy on the left, this is a low concentration, therefore very little, and I'm going to say no, no attractive forces. So this gas here will pretty much act ideally. Gas at high concentration will not act as ideal as you like, because at high concentration, even if you have a low pressure and a high temperature, there's still so many of them that they're going to notice each other. It's kind of a noticing thing. This is a high concentration. There's going to be attractive forces going on. In a very concentrated gas sample, they're not going to act as ideal as we like. And that's the last of Chapter 5.